out of some lectures on TEM examination of nuclear reactor core materials, I want to have another presentation here, which is going to focus on the interpretation of images and the effect of artifacts, basically mistakes that one can make when examining materials using the TEM. I had this slide at the beginning of the previous two lectures on diffraction theory, basically just to summarize the two main modes that one would use for TEM. One is imaging mode, where you get an amplified image of the microstructure. In a transmission mode, you shine the electrons through the material. The material interacts with the electrons, and at certain points where you have dislocation loops, for instance, or dislocations, that you get strong diffraction, and that then can be collected. The information from that diffraction can be collected and put together in an image in the microscope, a magnified image. At the same time, you can take that same diffraction information, basically diffraction coming out at a certain angle, to show what the orientation and the diffraction conditions are at that same point. And this shows that we have this is the main beam and this is the diffracted beam. So in this case, it's hexagonal and it's a 1,1/2 reflection. For comparison, we've got X-ray diffraction. X-ray diffraction is very different from TEM because there's a weak interaction between the X-rays and matter, and essentially diffraction amounts to scattering, and where you get constructive interference of the scattered waves, whereas in TEM, the scattered waves, or if you like, the diffracted waves, the waves that have strong interference, constructive interference, they can be diffracted, scattered, rediffracted many times as they pass through the material. And it's quite a distinct difference. This lends itself to a lot more interesting diffraction effects, which I've covered in the other lectures. And I'm going to focus on the images that one obtains and how you use them to analyze microstructures, especially in irradiated materials. So we've come a long way since I was a student, when this would be typical of a microscope. So as I was a student, the first 2 weeks when I was at Birmingham doing my PhD with Mike Loredo, there was one of my fellow students who'd actually been there for 2 years, but I don't think he'd learned anything. He was doing some irradiation in a high voltage microscope, and he came in on a Saturday morning, came up to me and said, "Look, I can't get any images out of the machine." And he said, "Will you look at it?" And even though I was way junior to him, I said, "Okay." And I went down, and there was an image. He showed me, there was an image like this on the screen. And I said, "Well, I can see that there is something there. And what are your diffraction conditions?" And he didn't know what I was talking about. So I put it into diffraction mode and tilted the sample a little bit to get stronger contrast. And I said, "Oh, well, you have damage, and there it is," and that sort of thing. Now, I don't have those actual images from that day because it was a one-off, on the spur of the moment. But these images I'm just showing you are pertinent to current day. They were taken from basically this region and this region of an irradiated steel. And this is some work by Onshi et al. And what they're looking at is basically channeling. So they wanted to show in this particular case that what some people sometimes misinterpret as dislocation channels, and I'll explain what they are in a minute, are often mistaken for mistakenly identified as channels when actually they're twins. And they were mistakenly identified as channels because channels involve clearing out of radiation damage, basically dislocation-free regions of the material. And it would appear like these bands are dislocation-free. It's not that they're dislocation-free, they just tilted to a different orientation. And you're not getting strong diffraction contrast, whereas in the matrix you do get stronger. It's not very good diffraction contrast, but it's stronger diffraction contrast. And really this difference between some contrast here and no contrast there is simply strong contrast there and no contrast there. I realize I need the pointer, not my mouse, to show up. The difference between these regions is not because there are no defects in this region, in this channel. It's because this channel is the crystal is tilted to a different orientation, and this is shown here where Onshi tilted it and shows up the contrast because it's a twin. It has a different crystal structure, and you have to tilt it to a different orientation in order to get strong contrast at the twin. Whereas in this case, weak contrast in this twin, stronger contrast in the matrix. In this case, strong contrast in the twin and very weak contrast in the matrix. So anyway, it's just an example, and it's probably more common than I would care to imagine amongst anybody using a TEM. They might look at that and say, well, we don't have any radiation damage there, but there's actually lots. Or they might look at that and say, oh, look, there's a channel cutting through the radiation damage. It's not really, it's a twin. Now that twin may have formed after radiation during mechanical testing, or it could have been there to begin with. And basically, if it was there to begin with, you just have, either way, you'd have damage within this twin. But in this particular case, it's obscured by the strong diffraction contrast of the twin. Oh, yeah, interesting fact is that in irradiated steels, for instance, T.S. Björn had done some work, and he showed that twinning was actually more prevalent than what is called shown, what one would imagine as channeling. It's easier to twin a material when it's irradiated and full of dislocation loops than it is to perform or not to have channeling. And I'll have to explain what channeling is in the next few slides. And for that, I'm just going to talk about radiation-induced defects in austenitic alloys. So what we have here in T.S. Björn's work is actually examples of twins in irradiated steel, 316 low nitrogen steel, and these are actually twin bands. They've identified them as twin bands. The issue here is whether they formed before or after radiation, and the only way you'd know that is if you can see an effect on the dislocation structure, because twinning will shear the existing dislocations or dislocation loops into a different orientation, which is likely to be an irrational diffracting vector. I'll talk a bit more about that as we go on. So in many cases, when people are looking at the microstructures of irradiated steels after irradiation, they often identify complex structures, and they're often identified as a mixture of twins and dislocation channels. So I haven't described what a channel is or explained what a channel is, or a twin, in fact, but I will get on to that. Just all you need to know right now is that there are two types of defect which can be misinterpreted, one for the other. One is a channel and one is a twin. No misunderstanding here. These are dislocation channels. I don't have the extra image I would have put on here. Dislocation channels are the characteristic of dislocation channels is that they contain dislocations and they have some the edges are not sharp like a twin would be. They're kind of they don't have sharp edges because of the dislocations. So what is the characteristic of channeling? Well, and twinning, in fact. So any kind of bulk shearing, which basically gives you a large strain jump at a particular point when either the twinning or the channeling occurs, that's a strain jump, and what that corresponds to in a tensile test is a load drop. So if you have a tensile rig, a load frame, and you're pulling some samples to failure, whenever you get some of these channels formed, you get a load drop. So in this particular case, they're channels, and you can see the kind of messy images that you get. This is some work by Bennett. This is from Lemeño and Company. And basically, what the channeling does is that you end up with a load drop and continued strain. There will also be some work hardening involved here, but it's because we're talking about engineering stresses, it's difficult to decide how much work hardening there is. There'll be some in the matrix, but also some in the channels themselves. Irrespective, all you need to know is that characteristics of the channeling is this load drop. Characteristics of twinning is also a load drop. So again, that doesn't distinguish one from the other, but it's a common feature for both. So what I mean by channeling, in channeling, what's happening is that if you have a dislocation loop, which is a basically extra half plane in the lattice, and again, I'll talk a little bit more about the makeup of dislocation loops in a little further on. What happens is that you've got a dislocation gliding through the material, and it interacts with a loop. Here's the dislocation moving in this direction. It's moved forward. It butts up against the loop, and then there's the loop, the original loop, and it passes through it. And in doing so, it subsumes some of the loop, the extra half plane of the loop, into the half plane, which is the dislocation, and continues on its path. In that way, you can eventually clear out all of the dislocation loops. If you have enough dislocations passing through the material and climbing, they'll eventually interact with and sweep out most of the loops. Here it is shown schematically. This is some work by Steve Zinkel and one of his students. Forget his name, something like Murphy or something. Anyway, what they showed is they just modeled that basic mechanism. So you have a source here and some in an irradiate material and some dislocations emitted on one slip plane. But the more that they interact with the loops, they climb. So you get this climb of the dislocations, and the dislocations continue. Now, as they continue through the matrix, they climb even further, and you get a distribution of dislocations, which is non-planar. And eventually you'll get much more alignment of the dislocations. So let's say that they butt up against a boundary or some barrier. You end up with this kind of structure. Now, the characteristic of dislocations that are arranged like this is that essentially it's a tilt boundary, and there's a tilt in the crystal as a result. There's no tilt from the shear of individual dislocations on one slip plane, but when the dislocations exhibit climb, it is climb that gives this tilt property to the dislocations in the crystal. So this is something that John Nye recognized many years ago, and he wrote a paper about it in about 1953 or something like that. And basically, although he didn't emphasize it, and that's the pity of it, it's really the geometrically necessary dislocations, which are the ones that Nye identified, are basically those that have some degree of non-conservative motion. They've climbed. So basically, slip alone, shear on one plane, does not change the tilt, but shear with climb can create essentially either tight subgrain boundaries or diffuse subgrain boundaries, and you end up with some tilt to the crystal. The only other way to create a tilt in a crystal from one single slip plane operating without climb, let's say we're just looking at these dislocations, is if you have a barrier and some constraints so that you end up with some elastic bending of the crystal. So I showed the one kind of process for clearing out of radiation damage, which is the channeling effect, and that is to be compared with twinning. While the channeling I just described gives a bulk shear, twinning is also a bulk shear. Well, twinning, the main characteristic of twinning is that it's a bulk shear, and that arises from the passage of partial dislocations on each successive slip plane. And that gives you a change in orientation of the twinned crystal relative to the parent material. And that's to be distinguished from slip, because slip typically involves a perfect dislocation, so you'll get one partial and then another partial, and a dislocation will move from this point to this point, which is a perfect lattice distance, whereas shear on each successive planes involves a partial movement, a partial shear on each plane, and because all the planes are shearing partially on each plane, they all basically are in register as one crystal, in this particular case with no faults, but there's a fault that exists at the shear plane, at the point where what we call the first undistorted plane. The second undistorted plane in twinning parlance is, and I don't have an example of it here, I was in another lecture about twinning, is the plane, is whatever plane is recognizable as the same plane before and after the shear. Now this represents a cubic crystal, and for the cubic crystal, all the planes are undistorted after the twin, after the shearing operation. But in hexagonals, that's not the case. The lattice, and also in BCC crystals, the lattice is distorted except for a few planes which are basically recognizable as the same planes before and after the shear. And in those cases, the material has to shuffle to reform behind the what would be called the second undistorted plane. Now, I just realized I should have maybe put something about that in here, but that's a different lecture, so I'll leave that alone for now. So the misconception about twinning is not just limited to how one interprets the TEM micrographs. It also occurs in the interpretation of mechanical effects. So here's an example from Garner et al., where they report on something called channel fracture, and what they imagined is that when you irradiate a material and you look at the strength, the mechanical strength as a function of fluence, then at fairly low doses, with no irradiation, it's highly ductile. There still retains some ductility at intermediate doses, and at very high doses, the fracture tends to be more intragranular and flat platelet. Now, Garner and company interpreted this as, or called it, channel fracture. And because in the same sample they saw evidence of shearing of cavities, like voids in the material that's in stainless steel, they put the two together, I think mistakenly, but they said, well, we get to this position and we also see this, so this must be caused by that. And that's not, strictly speaking, correct. So in this case, what you have here is a bulk shear, and the bulk shear has done something to the cavities. It's elongated them and smeared them out, and that's a bulk shear, and that's what you get from twinning. Now, what Garner and company did is we said, well, this is from channeling, from dislocation channeling, which is also a bulk shear. Either way, there's no kind of conceivable way that means cracking and failure on the plane. You have to make a magical leap of faith to associate that, which is a bulk shearing effect, and that, which is failure at an interface. Basically, it's a planar cracking, planar failure. So I think they misinterpreted it, hadn't thought it through. And if they had thought it through, they realized, well, we don't know the mechanism, how it would get from here to here. And they just state it. And it's amazing how many people just buy into that. But really, it's kind of nonsense in a way. And one of the reasons that I can make that kind of statement is in the same material, in the same work. Garner and company also, I guess the microscopy also said, well, I'd like to put this information in there. And that was some of the archive material for that steel sample that was irradiated. There were some grains, and so not all grains. It's like deformation is very non-uniform in most engineering materials. In some grains, there was evidence of what was identified as epsilon martensite. Queens, Puyang Chengisian did some nice work to recreate the deformation of Inconel X750 spacers, and he was able to show that you get the same kind of planar features which were identified as nano twins, but they could also be martensite. In this case, the planar features were identified as epsilon martensite. Here they were identified as nanotwins, but I'm not sure that there was a lot of detailed examination to prove that they were nanotwins. Maybe there was. Irrespective, even a martensite shear or a twin shear, it's the same effect, and what you end up with is a boundary along which the material can fail. So in any complex deformed structure in steels, and this is 3 or 4 steels, often it's reported that the structure consists of a complex mixture of twins, dislocations, and martensite. The epsilon prime is here. Now, in this case, they've identified something called alpha prime, and it was not clear what they mean by alpha prime, because alpha typically means a ferrite, and alpha prime is not necessarily is a quenched martensite where you've quenched in carbon. So I'm not quite sure what's going on here, although it is conceivable to go from the epsilon martensite, which is the hexagonal phase, to a body center cubic phase by shearing. So basically, you can go from an FCC state to HCP platelets, which is the epsilon martensite. And then if these hexagonal close packed martensite platelets, the epsilon platelets, also deform, in addition, there is a possibility of transforming a martensitic transformation from the epsilon to the what I would think of as alpha, which is the ferrite, the BCC phase. The alpha prime, calling it prime, I think is a misnomer, and I think that's linked partly to a lot of confusion in the literature where many people who report on microstructures who are not totally fully understanding what they're saying often just refer to martensite, and really what they mean is there are three types. I mean, possibilities certainly in steels, in 300 series steels, you can have alpha prime, alpha coming from epsilon, and the epsilon, so starting from the FCC phase, when you deform the FCC, it's possible to get epsilon martensite, which is a transformation from FCC ABC stacking to hexagonal close packed epsilon martensite, which is ABA stacking, and from there, from the hexagonal phase, you can also have another transformation if you continue the deformation to create BCC alpha, and I wouldn't call it alpha prime. I mentioned that there's confusion often, and here's another example where, to me, these are clearly either martensite plates or twins, and these authors have chose to identify them as channels. And often vaguely identify things as channels, whereas really there may be some channeling going on, as T.S. Bjorn and company had shown. But often there are reports of kind of channeled structures where people just say deformation bands. I guess that's because they don't know what it is. And they say like mainly slip bands, but I would say, well, that's not a slip band. That's either a martensite plate or a twin. So T.S. Bjorn and company correctly have identified mixtures of twins and channels, and I'm not sure that everybody is as well versed in the interpretation of the TEM images. And when you see a statement and people haven't provided information about, and we did this, we did tilting experiments or some other supporting evidence for the statements that are made, often incorrect statements are made. So you have to be careful. Okay, so I guess in the same vein, the interpretation of what causes fracture in steels and nickel alloys, that is fraught with difficulties, and mainly because often, especially in power reactor where there's a high thermal neutron flux, it's often possible to get a lot of helium generated, even in steels, in particular in nickel alloys. And I guess historically, a lot of these, the bubbles that exist because of the helium have not been identified, primarily because they're small, typically certainly at reactor operating temperatures, around about 300 degrees C. They tend to be small, maybe less than 5 nanometers, typically 1 to 2 nanometers. And historically, people haven't identified them. I think in part because you don't use your best microscope to examine irradiated structures, and typically people would use old equipment that's not very well aligned and doesn't have the resolution to image bubbles. But in this case, this is from some work from 2005, Danny Edwards and Fujimoto et al. And this was the first time when bubbles were identified decorating grain boundaries, and that can then be associated with the fracture mode in some of the slow strain rate tests that were applied to these materials. Now, at that time that this came out, and it was kind of a revelation in the mid-2000s, it was believed that people hadn't been aware, were missing the fact that a lot of grain boundaries were decorated with cavities because they hadn't gone through focusing. But I know, having experienced the same, not confusion, but the same, having had to address the same issues in Inconel, and seeing the effects, this isn't about focusing, it's about the alignment of the microscope. So if you have a well-aligned microscope and you're basically well aligned for high-resolution electron microscopy, and in paying particular attention to the stigmators, if your objective stigmators are nicely aligned, you will see these bubbles. I mean, you'll see them with better contrast as you go through focus because of the Fresnel fringing that one observes. But you basically, it's not the fact of doing the change in the focus that's important. It's the fact that your microscope is aligned. So one of the things I've noticed is a lot of work, especially with stress corrosion cracking, that's been conducted in the last 30 years, I would say, it focuses on chemical changes at the boundaries, at grain boundaries, and very ambiguous explanations for stress corrosion cracking, for instance, or what was causing it. And I noticed this particular figure from work by Steve Brummer and company, and it seemed to me that they got this measurements of chemical depletion and segregation at the grain boundary, and they had a micrograph beside it. And I'm looking at the micrograph and I said, ooh, well, that looks like your objective stigmators are slightly misaligned, but you've got enough contrast that, and maybe a shift in the image from where these things sit, but you've got enough contrast to make out bubbles. But I don't think that was recognized in the time. I'm stating it now. I think that's evidence that the grain boundaries are segregated, have bubbles aligned along them. Or the boundaries are perforated by bubbles. Now, the segregation, again, that's something that's been very ambiguous, flaky, how it's been interpreted. And I think a lot of that often is because people were not aware that you have this sink on the boundary. So when you radiate and you create helium, helium is very mobile, and it is not absorbed by grain boundaries like vacancies are, but it will migrate to the boundaries and stick there. You'll also get helium bubbles in the matrix, but if you have a sink where the helium is captured, what happens is then the vacancies that are floating around in the matrix will preferentially be absorbed by the helium. These helium bubbles will grow because there's a reduction in energy, in the surface energy, by allowing vacancies to be absorbed by the helium bubbles. And the diffusion of vacancies to the bubbles gives you a chromium depletion. So it's local diffusion of vacancies to the bubbles. And that's because chromium is a fast diffuser by a vacancy mechanism. So in the case of irradiation, when you have radiation and a vacancy sink, what that means is that you'll get preferential depletion of chromium from the vacancy sink. The same applies to iron, by the way, because they're equally fast diffusers. But nickel and other elements like tin, it's not here, but I guess it's silicon, they're not as rapid. Even though you get this depletion of chrome, it looks like you're getting segregation of these others, but really that is misleading, because simply by having a depletion of chrome and iron, you increase the relative concentration of the other elements. Anyway, I'm just saying that it's really off the top of my head. I'm not being very I'm being a little bit glib about it. It's kind of what I think is going on, but I can't prove that because I don't have the samples and I can't verify it. But it seems to me that that's something that should have been looked into, or can be looked into in future. And I suspect that a lot of cases where researchers were examining materials and saying, well, that material cracks easier than another material, they're not taking into account the fact that the materials have boundaries that are perforated by bubbles. It's not just grain boundaries, it can be twin boundaries or martensite boundaries, any kind of interface. So talk mostly about steels there, so now I'm going to talk a little bit about nickel alloys, for which I have a lot more experience. So in nickel alloys in CANDU reactors, when you go from an unirradiated to radiated state, they exhibit very profound intergranular failure. And that's because in a CANDU reactor, we produce tens of thousands of atomic parts per million of helium over a 10 to 20 year reactor operation. So after 30 years of operation in a CANDU reactor, so 24 effective full power hours in a CANDU reactor, there's something like 30,000 atomic parts per million of helium generated. So the reason I mentioned about having the microscope aligned is because when we first were having evidence that we're getting a lot of intergranular fracture in our spacer materials at Inconel X750, we had the benefit of seeing that the earlier work in the mid 2000s from Edwards and Fujimoto of helium bubble segregation on boundaries. So the thing to do would be then to polish a sample and then look for these bubbles. So here's an anecdote, and just again, it's a warning. It's like a lesson I'm going to tell you about. I was a manager to initiate this program and said, well, we have to do this. And I assigned people to do certain things, to prepare the samples, to examine them, and this kind of thing. And about 6 months into the program, the first sample had been prepared by electropolishing, which is very difficult considering the sample was tiny. The first sample was being prepared, and I got a call in my office, and there was half a dozen researchers over in the TEM lab, and they called me, and I went over there, and they said, they kind of laughed and said, what you thought was going to be, we were going to see, which would have been cavities on the boundary, we don't see it. So you were wrong. You have to think of something else. And I scratched my head and I thought, well, that doesn't look right, because the image didn't look like a very sharp image. And I spent 20 minutes at the microscope, and then bing, there you go. And so I turned around and I said, oh, there you go. That's they are there. You just didn't have the microscope aligned. You have to spend the time to, and when I say align it, I don't mean just focus it. I mean align the objective isotope for basically reduce all of the just have a well-aligned image, and in particular the objective stigmators. So you have to have your optic axis correct, and you have to have your stigmators correct, and then you can see the evidence, because you won't be able to see this unless the microscope is set up for high resolution imaging. So this is the same images using under focus and over focus. This is the very first image that were generated from our spacer materials in Canada. And this is from that day that I went over, and I said, well, let's check and see what we have. And we have this under focus, over focus criterion to show that they exhibit Fresnel contrast, but that isn't actually, I'll talk about this later, that isn't sufficient to know that these are cavities. Because if you have deposits, surface deposits, especially amorphous oxide surface deposits, it'll show the same contrast. So you have to be careful. You have to basically take stereo images, and I did in this particular case, because it was important to me to know that these were real and they were in the bulk of the material. So I took stereo images in this particular case, and I satisfied myself that these cavities were in the foil. They were in the bulk of the material, as well as these being on the boundary. I mean, you can deduce that they're higher concentration because the density is higher. So you can deduce that you have a higher planar density of cavities, comparing this to this. But, that's just reasoning. But even then, you want to be absolutely sure using stereo microscopy that they're in the foil. So why do we get that boundary segregation? It's very important whenever you're getting evidence of intergranular fracture. And that's because helium, when helium is created in the material, you get a certain amount segregated at the grain boundaries. So you not only have helium forming, combining with vacancies in the bulk of the material, but you have excess helium segregating at the boundary. So if you can imagine, if a helium atom that comes to rest at this point in the location after it's been ejected from a nickel atom and comes to rest as an alpha particle here, it's got a high probability of being absorbed by the boundary. But it isn't absorbed actually, because it's a helium atom and it's very insoluble. So it doesn't contribute to climate dislocations in the grain boundary. So basically it migrates to the boundary and sits there. But because it has a high pressure, it then absorbs vacancies readily, and the surface energy of the resultant bubble can be lowered by absorbing more vacancies. So simply because helium migrates to and sticks on the boundary means that you get more vacancies migrating to the boundary and giving this perforated structure. If you look at ion irradiation, in an ion irradiation case where we don't have helium, any vacancies getting to the boundary are simply absorbed by the boundary. If you think of the boundary as a network of dislocations, the dislocations simply climb. And interstitials will also migrate to the boundary, and they'll climb in the opposite direction. But basically, when you have no helium, the grain boundaries are clean. So this is just illustrated here. So in the one case, vacancies which form cavities in the rest of the material are absorbed by grain boundaries, but not when helium is present. So another example of misinterpretation of images is this one. This is also from the Inconel. So in 2018, I was at a meeting and some researcher got up, presented this image. It's an EBSD or a thin foil, a fibbed focused ion, a foil produced by focused ion beam of a microtensile tested sample. And what they observed is crack moving in this direction. So we get a crack forming along an interface with something here. And being in the audience, I said, well, what is that? I see something. It's not clearly in contrast. So you haven't tilted it to the right conditions for giving the right diffraction contours to know what it is. And the guy just said, oh, it's a slip band. And I'm thinking, oh, that doesn't make sense at all. Because anyway, it just didn't make sense. And one of the reasons is when you have a slip band, the edge of the slip band, which you think of as an edge of a slip band, isn't really an edge. It's just where the plane, which is the slip plane, intersects the foil surface. So you have a big wide plane and you're taking a slice through it. And hopefully I've got that here. So it's not a slip band, it's something else. So this just helps to illustrate that. You've got a slip band, dislocations moving on a plane here, and then we take a thin foil when the plane's inclined, and we see what is an apparent edge of the slip band, where the slip plane intersects the grain boundary. And this is illustrated here. I took this off the internet, and we see discrete dislocations, and where the dislocations or the slip plane coincides with the surface, we basically see what looks like an edge. And then this mistakenly, not mistakenly, I guess this thing then appears as a band or a channel, if you like, and it's not. It's just a slice through something. And there's certainly no change in the orientation of the crystal. But that was in a meeting where I said, well, that doesn't make sense. I don't believe that that's a slip band. Everybody else at the meeting said, well, we believe the person who said it was. And I said, well, that doesn't make sense. So fortunately, from the same laboratory, another worker years later got the same sample and produced some images from the same sample. They're doing some examinations to look for the dislocation structure and whatever. So on the left-hand side is imaging with basically which helps reveal the cavities. It's basically poor diffraction conditions, so you can reveal the cavities and absorption contrast. It's a much better condition for revealing the cavities. And on the right-hand side is more in a diffraction contrast condition, but it's the same feature. And this is the same feature as that. And what it turned out to be was a collection of platelets, which is twins. It could be twins, could be martensite. They're kind of too small to analyze. Now, this is only 20 nanometers wide. And one of the arguments that was posed to me at the time when I said, well, there you go, that's what it is. We're getting cracking down this platelet interface. And then somebody said, well, that's because it was created during the testing. And I'm thinking, how do you know that? It's because we did an EBSD scan of the sample before we tested it. But then again, I pointed out, look, this is 20 nanometers wide. You're not going to see that for a typical spot size you would use when you're doing a scan to determine where to do your microtensile test. It's not going to show up when the probe size is 100 nanometers and bigger. It just won't. You might see some vague evidence of a feature, but no, you won't see it. So here's the image in a little bit more detail, so you can see where this cluster of platelets is. Now, I don't know what they are. They could be twins, could be martensite, but it's a sheared. These are sheared because there's no chemistry related to that. That touches on another thing that's come up more recently. Is somebody said to me, well, we've got. How do you know you've got martensite? And I said, well, because it's hexagonal and lots of people report martensite. Well, it could be something else, and basically adaphase. So in nickel alloys, you have what's called adaphase. So adaphase is a fully transformed state of what would be the gamma prime. So it's nickel 3 aluminum. But what you would have when you have adaphase is platelets of adaphase, is you basically would have the chemistry signature. And I'm not aware that there is a chemistry signature related to this. So that's the one thing. If you have platelets, in order to decide whether, or is that a precipitate or is that a deformation, twin or martensitic plate, you look at the chemistry. And if the chemistry is uniform and it doesn't identify as a precipitate, then it's going to be a twin or a martensite plate. Anyway, so this just illustrates this structure and what was identified as a slip band, which is basically nonsense. So not a slip band. And that cost me a lot of ridicule because I said, it's not a slip band. So how do these things show up, these platelets? So once you've produced them, let's assume you've done that from the fabrication. When you create a fracture surface, as you have here, they show up as protrusions because they're hard, and you get cracking along these platelets. I've seen similar things where in stress corrosion cracking tests, and people see these protrusions at the surface and said, aha, that's because of localized deformation. Not necessarily. It could be the same thing as that channel fracture. You just have defects that are in the material that you weren't aware of. Now, you may not have been aware of them because you didn't have the resolution to image them with whatever imaging system you're using to begin with. Or it could be that even if it was a TEM, which would be a high resolution, in effect, you should be able to see them. Even if it was like that, features like these are not uniform necessarily. You might see them in some grains, but not in others. So unless you're doing a very detailed, thorough study of all of the defects in every grain, you wouldn't necessarily be able to state categorically that these things were deformation induced. And in this particular case, no, they were part and parcel of the microstructure prior to testing. Actually, this was not just testing, it was helium implanted and then tested. So what this says to me is that we get some segregation, some perforation of the boundaries, and when we do the testing, it's a little bit more brittle, and you get failure, ultimate failure, where you get helium segregation at the interface. You don't need to have the helium segregation, but it certainly helps to have, well, the interface is the important thing. And if you have helium, that just makes it weaker. So the reason I say that is because even unirradiated material, you can have bands of what, in this particular case, they're stringers, what's called stringers. It's the bands of impurities. So this is just precipitates, bunches of precipitates that are segregated in certain regions. And when you have an impure material like this, you get that same lowering of the ductility, even though you might have, and it's because of, which can be very definitely associated with these inhomogeneities in the material. And if you don't have them, you get much better response and it's more ductile. Touching on the other thing I was talking about identifying this slip band as, or this band as a slip band. Here's that same feature where there was cracking further down into the foil. And one of the other things I pointed out said, well, it's bent. And I got so many excuses from people bending over backwards to say, forgive the pun, why a slip band could be bent. And I've seen that kind of nonsense in many cases. I've seen this scientific advisor of the UK government come and give a presentation at Chalk River, and he showed some little loops, which he said were punched out loops in an arc, and I pointed out, I said, that can't be. Those are not loops. I don't know what you are. You're looking at the end of a subgrain boundary or something, but those are not punched out loops because. And he said, why? He said, because I said they'd be straight. You have a line of them which would be straight because the loops are basically travel in a glide cylinder, and the glide cylinder is restricted by the slip direction. So you'd have to have some weird climb, slide, glide, climb mechanism, which is unlikely. Anyway, there are many other possibilities that clearly were not explored before making the conclusion that it was punched out loops. Anyway, in this particular case, same deal. The initial conclusion was that this is a slip band. Oh, and it was. And the failure, the cracking, occurred because you have this bulk shear. It was the same argument that Garner had about channel fracture. So you have this bulk shear, which could be twinning or a localized slip band, doesn't matter. It's a bulk shear occurring. And that was associated with the cracking, whereas really it was the twin martensite platelets that associated with the cracking, and this was just secondary. So this is where it's important not to jump to conclusions. Oh, I see that, I see cracking, and therefore this cracking is related to that. There are other things that can explain the cracking, and it's not necessarily this channel fracture or even twin effect. Anyway, there's just no conceivable mechanism where, well, there's a very extremely magical thinking mechanism where if you get shear on one plane and if you get enough overlap of enough cavities that they essentially form something that's akin to a crack, maybe, but no evidence of it. So in the absence of any evidence for it, just simply seeing something and then saying, well, I imagine that leads to something else, is not the right scientific way to approach these examinations. So geometrically, it's inconceivable when people talk about channel fracture based on these sheared cavities. Well, that's just an example schematically how a twin would shear the material and what would happen to the cavities. So they're all shearing at the same time, and basically in the same direction. So it's very hard to get any overlap when it's a bulk shear like that. Anyway, no evidence for any crack formation from shearing of cavities. Okay, a little bit more about TEM. I gave a couple of other lectures where I talked about TEM theory, but I want to focus more on interpretation of images in this particular presentation. But I'll talk a little bit now about diffraction in the TEM, just as a reminder. In diffraction in the TEM, a bright field image is obtained by selecting a certain region of the diffracted beam. So we have the direct beam, which is shown here, which is coming direct through the sample. So the dotted line is the plane that's diffracting, and the Bragg angle is a fraction of a degree. It's small, very tiny, small in an electron microscope. So we've got the direct beam coming through, and if the direct beam is focused, we can create an image, and focused, in the back focal plane of the objective aperture, and you therefore of the objective lens, and you therefore select that image. You select that intensity to create your image. You're basically throwing away anything that's diffracted off at an angle. So basically, if you've got any parts of the material which are strongly diffracting, like going where the intensity is now being deflected along these red lines, they're being buried in the aperture, and that shows up as a dark part of the image. We're throwing away the intensity, so everywhere else is light except for where we're getting diffraction. Likewise, if you take those deflected or diffracted beam and collect the intensity from that, where it was dark in this image in the bright field, it's bright in the dark field image. And phase contrast, which is what you would normally have for imaging cavities, small cavities, bubbles, or atoms, whichever you want. The essence there is that you collect all the information, you have a nice large aperture. So we're seeing interference effects in this particular case. And the larger the aperture, the smaller is the theoretical limit of the resolution. Oh, I'm not going to get into this because I talked about it in other lectures, but basically when I talked about the electron beam coming in or coming in this way, it interacts with the sample and you get a strong diffracted wave out at a particular angle. Two characteristics of this angle is that the angle of incidence is equal to the angle of reflection, and you get constructive interference, plus the angle is such that it has a certain geometric arrangement relationship with the scattering from atoms in each plane or in separate planes, such that the phase difference, so that you get constructive interference, the phase difference is 2d sine theta. Now that phase difference can be some multiple of lambda, it can be 1, 2, 3, 4. Talk a little bit about gamma prime, because that's a common interesting thing about gamma prime. In the other lectures, I talked about structure factors, and this comes into play with gamma prime because one of the things that is an interesting feature about gamma prime is that it has superlattice spots. So normally in a cubic material, whether it's FCC or BCC, you don't get any diffraction at what would be the O1, in this case 010, at this point where we see that bright point here. And that's because just turns out that you get constructive and destructive interference, and there's half of the atoms are lined up so that they cancel the scattering from the other half. So for half the plane spacing, this is the 010, for half the placing 020, you get strong diffraction. And even though in nickel 3 aluminum and the gamma prime, we're basically talking about an FCC crystal, the fact that the atoms are ordered, that's the reason why we get some intensity. So if we just had a uniform distribution of atoms, either they were all nickel atoms or the aluminum atoms were randomly distributed, there's no distinction between the density of the atoms on each successive plane here. This is the one. This would be the 100, and this would be the 200 plane, and you get no contrast. But because these atoms here on the what would be the 200 plane, because they're nickel atoms in this case, when you've got aluminum atoms at the corners. So you have nickel 3 aluminum in this particular case. Because of that, there's a difference in the atomic scattering factors from these atoms, and the contribution turns out to give you a net intensity for that 100 reflection. Another thing that people should be aware of is double diffraction. So if you have a very dense zone axis where you have a lot of reflections, because of the nature of dynamical diffraction, where the diffracted beam can be rediffracted back into the main beam, but also be rediffracted into other beams. In some circumstances, you get these extra spots where they shouldn't exist based on the structure factor. So just be aware of it. Double diffraction effects. The way to distinguish the double diffraction effects, the first and easiest way to know that you have that point here is double diffraction, is looking at the Kikuchi lines. So basically, the Kikuchi lines, we'd only get Kikuchi lines corresponding with these wider separation of the diffracted spots, and you don't see any Kikuchi lines with the shorter ones. That would make a lot more sense if you saw the other lectures I'd given. Okay, talk a bit about radiation defects. I'm going through this kind of without digging too deeply into the diffraction theory, and I hope you know enough or can pick up enough to get something from what I'm talking about. I mentioned dislocation loops previously when it came to the mechanism of channeling. And that only occurs if the loops are glissile, if they're perfect loops. So if they're folded, that doesn't apply because they can't be subsumed into a glissile dislocation. But what do I mean by a loop? Well, a loop, this describes loops in hexagonals. Typically in hexagonal, in zirconium in particular, you get loops possibly on basal planes or on the prism planes. So this is the hexagonal prism here, and you get loops on this plane or on this plane. But what happens in zirconium, for instance, is that these loops tend to be vacancy in nature. And they would show up when you're imaging, looking parallel with the basal plane as little lines, because you're looking at them from the edge on. On the prism planes, you get a mixture of interstitial and vacancy loops, And if you looked at, they typically don't tend to be, you can't get them edge on because they're actually glissile. They're perfect. A third 1 bar to ore, and they can move around. They'll tilt and they'll move around. So it's very rare that you'd see a prism plane glissile loop in an edge on configuration. These are edge on because they're faulted. So basically they don't leave the plane. And these are just an example, just to show a bit more schematically. Vacancy loop, we're taking material out from a certain region of a plane, and in interstitial loop, we're shoving in a plate of material. And it distorts the lattice accordingly. Oh, yeah, I don't really want to talk about this necessarily, but for the other, in some of the other, one of the other lectures, I talk about defining the loop habit plane. Suffice to say, we use the finish start convention. And suffice to say, if you're looking at a vacancy loop like this, and define the Burgers vector according to a certain criterion with the FSRH criterion, the Burgers vector is pointing downwards, and an interstitial loop, the Burgers vector is pointing upwards. So once you have a dislocation loop, so here's an interstitial loop, the Burgers vector is pointing upwards, and the Burgers vector is pointing downwards, we can make certain measurements and decide what the character of the loop is. On the one instance, if we look at certain planes with respect to the loop, in this particular case, one where the diffracting plane, which is that one, which has a vector which is perpendicular, the G vector is perpendicular to the plane, and I cover that in another lecture, and the B vector, when this plane, when the Burgers vector essentially is parallel with the plane that's diffracting, you get no contrast, whether it's an interstitial loop or a vacancy loop. But if the loop is tilted, and we look at other planes that have a certain orientation with respect to the plane of the loop, these are distorted depending on whether you've got an interstitial loop or a vacancy loop, as we see here. And when you set up the diffraction conditions, in this case where we have a S positive, and that basically condition where the diffracting vector is slightly larger than, or the diffraction angle is slightly larger than Bragg, then the crystal has to rotate into the Bragg condition, rotate clockwise into the Bragg condition to get strong contrast. So for this setup, you get strong contrast from this loop at this location and this location, and for this loop at this location and this location. So for this side of the plane where we're diffracting, that, let's say that's G positive, and let's say that's G negative, you change from inside outside to outside, from inside contrast to outside contrast, or if you keep the diffracting vector the same, a vacancy loop will show inside contrast and an interstitial loop will show outside contrast. Didn't explain that thoroughly. I have other lectures that you can look at. Residual contrast. I mentioned getting zero contrast to define what the Burgers vector is. It doesn't always follow that the contrast is going to be zero. It depends on the line direction as well. In this particular case, when the line direction is parallel with the diffracting vector, you get this condition of zero contrast. But if it's perpendicular or inclined to the diffracting vector, you get some contrast. Loop analysis. This is some loops in electron irradiated zirconium. It just shows how you would do loop analysis for particular diffracting plane. We have these loops are not in contrast in this image, and I know that then that's a 1 bar 210 type of loop, because the G times the Burgers vector dot product of the G vector, the diffracting vector, and the Burgers vector is 0. And the outside contrast, I guess this shows outside contrast. Well, that's a different tilt as well. Sorry, no, this is a different tilt. I have a lot of other images for this case, but I can tell you that this is a vacancy loop. Kikuchi lines, don't want to get into Kikuchi lines. If you've done TEM, you'll understand what I'm talking about. When an electron comes in, it can interact directly, strongly with a diffracting plane where you have a lot of atoms, a high atomic density. If you've got the angle coming in at specific angles, which the Bragg angles, you will get strong diffraction coming out. But you don't have to have that orientation when it comes to Kikuchi lines, because any electron going through the foil is being refracted or distorted or scattered, and it gets scattered in all different angles. And what that means is that you get conditions where there would be whatever planes are close enough to that scattering that can be at the Bragg angle from these scattered electrons. What you'll do is then you'll get these cones of diffracted intensity, and what these do is that they're called Kossa lines, and they can be imaged on the TEM image, not the TEM image, in the diffraction pattern. So this is what Kikuchi lines look like. This is the basal orientation for zirconium, and this is what's called a Kikuchi map. And we navigate in orientation space using the Kikuchi map, bearing in mind that the Kikuchi lines represent some people call them tram lines, but they're lines that come out. You've got to imagine that these are like strongly diffracted beams of electrons coming out the bottom of the crystal. So that when you tilt the crystal, you've got to think of the Kikuchi lines as being attached to the crystal, but you're seeing the effect projected onto the bottom plate of the microscope, as if these tram lines are coming out of the bottom of the crystal. So you have to bear that in mind when you're driving around in Kikuchi space. Once you know where you are, there's certain characteristic orientations, certain diffracting vectors that help you characterize the loops. Here's an as-irradiated single crystal irradiated in NRU. Pretty poor contrast. And that's a characteristic of zirconium, because it's a heavy element. It's element 40, and often the contrast is anomalously absorbed, if you like. There's a lot of absorption to deal with. So one way to get around that is to heat the sample. And what I've done is taken that previous sample and heated it for an hour at 500, and we get a nice, a less finely dispersed crystal, and we can distinguish the loops much better. Here's an example in zircaloid 2. Oh, this is I don't know why I left this in. The loops don't develop with just any irradiation. You've got to build up the dose. So in this case, we're at this particular location here, this pink line is line broadening, and you see that there's enough. We don't see any effect on the line broadening, but we don't see it in the TEM. But if we keep going, by the time we get to F here, where we see a signal in the X-ray diffraction, we also see the effect in the image, the TEM image. Right. And this is a typical TEM image of a neutron irradiated zirconium 2.59 in pressure tube. The effect of the loops on creep, for instance, is shown here, and it shows that as the loop density increases to some saturated value, the creep properties change and eventually evolve to some steady state condition. So in this condition, the microstructure is relatively constant, and at this point, we're reducing the creep rate, the irradiation creep rate, I should say, and that corresponds with the point where the dislocation loop structure is evolving. I mentioned zirconium being a heavy element. Titanium is much lighter, and you get less absorption, and therefore the imaging is much cleaner. So you can do much easier loop characterization in the titanium. There are also vacancy loops here. Here's some example of the loop characterization. The only takeaway I want to point out here is that it's important to know the sense of the loop, how it's tilted. So when you're looking down the beam direction, which is defined as upward normal, when you're looking down on top of the loops, it's important to know whether it's tilted left or right, and because that affects the contrast. In this particular example, if we're using these planes, this set of planes to diffract, if our diffracting vector is not that way, it's pointing that way, we have inside contrast. And in this particular, oh, sorry, no, it's the same. This is keeping the same diffracting vector. With that diffracting vector, for this orientation, we have inside contrast, and for this orientation, we have outside contrast. So it's important to know what the sense of the loop is, so you can easily get misled. Here's a C-component loop in zirconium and the characterization of the loop. Here's some other loops in zirconium and their characterization, typically the vacancy, whether it's neutron or electron irradiation. I mentioned about cleaning up the image by annealing. In this case, took a sample with some C-component loops in it from a PWR. It's radiated around about 300 degrees C, and heat it for an hour at 600 degrees C. You get nice clean images, and it makes it easier to do the loop characterization. In this case, it's a vacancy loop. Here's a C+A loop. This is electron irradiation. So you get all kinds of neat and interesting stuff. And here's a basal plane loop with this Burgers vector. It's either a half O1 or bar 2 or 2 bar 3. Important thing here is that they're vacancy. This is electron irradiation, about 425 degrees C. You see them with this diffracting vector. They're kind of fuzzy. They're on the basal plane. There's stronger contrast here with this diffracting vector, and you have this residual contrast in this particular case with bar 1, 2, bar 1. You can see this little two lines of residual contrast. Characterizing of those loops particularly difficult. And my initial conclusion was that they were a half-hole bar one, but a re-examination in more recent years has shown that they can be either, and that's because of the ambiguity in knowing when you have the loops in contrast. I didn't say that very well. The reason I identified them initially as a half-hole one is because I couldn't see them here. I didn't know how to identify them. So for this particular set of conditions, I didn't use, at this particular orientation, I didn't use the information. And for that reason, rather than coming to the conclusion I should have been more ambiguous and said it was either one Burgers vector or another. And I just put in, and the reason for that is that we actually, like I said, it's important to know the tilted loop, but actually it's important to know everything about the loop, exactly how it's oriented, because the contrast can change from inside to outside contrast depending on how what your beam direction is. So because these loops are faulted, they always stay on the same plane. So what I'm showing here is different beam directions and essentially the same type of diffracting vector. So in this case, with this beam direction, I have outside contrast. And in this case, with this diffracting vector, I have inside contrast. Sorry, this beam direction and this diffracting vector. Anyway, what it means is that instead of being a nice simple analysis, half or bar one, it's actually 1/6 bar 2 or 2 bar 3, potentially 1/6 2 or bar 2. In fact, likely 1/6 bar 2 or 2 bar 3. The most important thing is it's vacancy. Basal plane loops are always vacancy. Often in neutron radiation case, the microstructure is too complex to make things out very clearly. And often with C-component loops, we rely on using the O2 reflection. When we use that, all the A-type damage, the prism plane stuff, the stuff on the prism planes of the hexagonal prism is out of contrast in this case, and we see the C-component loops, in this particular case, edge on. So we're actually, think of these as platelets that we're looking at the edge of the plate. What this shows is that ostensibly for the same neutron irradiation conditions, same temperature, in the same capsule, this sample, which is high purity zirconium, is not susceptible to C-component loop formation. This sample, which is impure, it does have a lot of C-component loops. So one can conclude that it's likely that in this particular case, specimen purity is a factor that has to be considered as to why these loops are stable. You don't just have loops, although they're the most common type of defects in zirconium. You still can also get cavities. Kind of rare in neutron radiated case, but if you take electron radiated material, even high purity material, and you irradiate the hell out of it, like to 100 dPa, you can eventually get cavities formed. They're here, and they're in layers parallel with the basal plane. Here's an example of cavities in zirconium. And as I said, they're rare. You might find them in a sample in 1 grain. And it's probably likely that that's because there's some impurities here that not only affects the C-component loops, but also the cavities. And in that particular case, it's probably likely that you've got some nickel close by, and you've got some or a boron, and you've got some helium generated to stabilize these cavities. I've talked a lot about I've talked a lot about mistakes that are made in interpretation, human error, and I'm going to carry on now. So some of the errors can be kind of genuine, can be forgiven because, well, unless you know more about the material, you have to get further on the Dunning-Kruger curve to get the experience to know, oh, well, that's not what you think it is. Although it's real, it's not what you think it is. Here's some faults that you get in zircaloy 2 within a twin. So there was a lot of controversy many years ago about whether you get faulted loops in zirconium. And in some cases, it may have been well, I wouldn't be surprised if anybody came across this kind of images in a zirconium that they thought they have some faulted loops. But really, this arises because you have dislocations and a twin sweeps through it, and they shear and drag a fault behind them. It's just an aside, kind of peculiar observation. True artifacts that really people should be aware of is when you have deposits on the surface. In the case of zirconium 2.5 niobium, both electropolishing and I think in FIB preparation, you tend to deposit niobium-rich oxide as little dots and little strings on the surface. And that shows up with Fresnel contrast. It's either bright or a dark image. But this is surface deposits. They're not cavities. I showed you earlier about cavities and that they can have Fresnel contrast, but these are not cavities. This is just amorphous crap on the surface. They'll show this dark, bright image. So anybody who says, oh, I have cavities, I did the Fresnel contrast inside, outside, they're dark here and bright there, that proves they're cavities. No, you still could be looking at a surface artifact. Where I use that fact to some value is when I'm looking at small precipitates in neutron radiated zirconium, niobium. So we have small precipitates, which are a bit fuzzy here because we're out of focus to show up the surface contamination, and they're dark here as well. So they're both similar contrast, even though different degrees of fuzziness. But that tells me that these are real, and they're it's a lot more difficulty than analyzing and proving that they're niobium rich, but I have done that. These are actually beta niobium, roughly 85% niobium. So the Fresnel contrast, as I said, is something which can be applied to cavities. These are some small cavities. Damn it, I've lost the. These cavities are only of the order of 2 nanometers, 1 to 2 nanometers in size. But what this image shows is that when you have a under focus, sorry, it's not, it can't be, you can't say, I can't say under focus, over focus. All I can say is that I have a different focus condition at a different point in the foil. So some of the cavities are under focused in this condition, and some of them are over focused. It's that one here. So this one here, this dark spot here is bright here. This one here, which is bright here, is dark there. And all that means is that there are different heights within the foil. So there are different heights relative to the focal point of the image plane. Here's the same image at a lower magnification. So that magnification marker is 20 nanometers, and the region I just showed you is up here. So that just gives you an idea of how small those cavities are. Here's another image showing the surface contamination and the effects on like these light, especially the wormy looking things here. They're dark here and they're bright there. But the precipitates, they're little dark spots that stay as dark spots when you go under and over focus. They're real precipitates. Colleague of mine from many years ago, Ross Gilbert, he's the one who made me aware of this in the first place. And he'd done some work back in the 70s tilting a thin foil because with it being zirconium, there was an awareness that, we shouldn't be seeing cavities. And it didn't look right because sometimes they have that wormy kind of appearance. And what Ross did was able to make a thin foil and he'll tilt it so far on edge and set up the imaging conditions in the microscope so you could actually distinguish the deposits. So some kind is more flatter, but on this surface it's more stalagmite type. Oh, this is what I mentioned, that once you've identified which are real precipitates, you then have to go through the rigmarole of proving that they're truly niobium rich. Oh, artifacts, here's an artifact C component. It's not caused by any structural feature which has a strain field distortion of the basal plane, but you have local bending in the foil because of the alignment of the damage, like rafting. So this what's called corduroy contrast is because of the periodic bending of the thin foil. I mentioned how C component loops were often there was quite a bit of debate in the late 70s, early 80s. Some people believing that C component loops didn't exist in zirconium, and some people believing that they did, and there was controversial round robins and stuff like that. And this is a sample from one of those round robins, and I noticed this on the wall of somebody's wall in the lab when I first joined, and the first thing I looked at and said, well, what's this here? And this was this micrograph was actually used in a paper to prove that there wasn't any C component loops. It was cut off here in the middle, and saying, look, we only have A type loops, but it missed this bit. And what are we talking about here? That bit there, when you look at it in higher magnification, you can see the fringes. And based on my experience, I said, oh, okay, what's happened here is that we've cut off a loop. We've just got a bit of a loop. We just got the edge of it. And the rest of it is basically has been polished away when preparing the sample. Another factor, if you like, this is more of an artifact. This is some work from when I was a student, electron irradiation. Because of electron irradiation in a high voltage microscope, vacuum wasn't that great, so the surface oxidation of the foil, and that surface oxidation gave what's called asymmetric contrast, so that in one imaging condition, we have a nice clean image and we can see the dislocation loops, and in the reverse diffracting condition, this way we see poor contrast. And although ostensibly we can see some of the same loops, it's very difficult to identify the loops in both images. And that affects the ability to determine whether the loops are vacancy or interstitial, because to determine whether a vacancy interstitial, you want and to know what the image is in one diffracting vector, in one direction, and compare it with the image in another. to see if one's inside and one's outside. You can see how in this particular case, it's essentially the same plane that's diffracting, and we see, for instance, this dislocation here, but it's very difficult to see where that dislocation is in this case. This loop here, yeah, there's probably something there, but I can't see very much. So it's very ambiguous then, the analysis. Oh, another thing about artifacts. Here's a few years ago, I was at a meeting in University of Michigan, and somebody had been doing some ion irradiation. The student got up and he said, "Look at this," and we did this ion irradiation. We back thinned the sample, and we got to where we thought that the damage layer was, and we prepared the sample, and we see, and they showed something like this, or something like this. Actually, it was closer to that. And basically, my question then to them is, well, based on my experience, they don't look like loops. They look like hydrides. And I said, well, how do you know that they are loops and not hydrides? And if they had any concern, what they could do is do some stereo microscopy to show that these are hydrides, because this isn't irradiated, it's just polished zircaloy sample. And they could do some stereo microscopy to show that these were on the surface. That is, they're an artifact. They're produced from the polishing. So many years ago, back in the mid-70s, this kind of image was produced as evidence of C-component loops in ion irradiated samples. So basically, that was a misleading statement, and they hadn't done the requisite amount of soul searching and imaging and thinking about the process to know that, well, what they had here was actually hydrides. Here's another example. Here's just room temperature electropolished samples of zircaloy and zirconium. In the zircaloy case, the hydrides are very small and uniformly distributed. In the zirconium case, they're much larger, and you see this punching out of dislocations. Now that comes about because the hydrogen is in supersaturated solution when it eventually precipitates. And if you have a site on the surface where you get a lot of hydrogen generated from water vapor or whatever, when you prepare these samples, and you're pushing a lot of hydrogen into the material, because hydrogen likes to be in the zirconium, if the chemical stress of the hydrogen and the concentration it exists at is higher than the yield stress of the material, you will get some deformation. So the deformation typically occurs when you've got the chemical stress, the stress driving the precipitation, and it's a real stress, is higher than the yield stress of the material. So although this is ostensibly on the left-hand side, this is zircaloy, although this is ostensibly the same conditions, temperature, room temperature, foil preparation, you don't see as much evidence of this deformation in this particular case. And that can be attributed to the fact that in this particular, the zircaloy itself is much stronger. The matrix has got a lot of tin in solution, and the matrix is much stronger. And that's probably why you get smaller precipitates. They definitely want to precipitate, but they can't precipitate as large because of as large precipitates because of the strain that they produced. In the softer case, single crystal zirconium, the material is soft enough that it doesn't really matter. You can get large precipitates formed because they can easily yield the material. Okay, so I think that's about it. Sorry for rushing through this. I just wanted to get some notes out about artifacts and pitfalls and points to look out for if you're doing any electron microscopy. I have a couple of other lectures on my YouTube that go into more detail of basically diffraction theory, and I wanted to keep off that in this particular case because I just wanted to show some examples of the pitfalls of doing electron microscopy. Here's a couple of YouTube channels you might want to look at if you're interested. That gives some background. This bottom one was more related to diffraction theory, and it's a really nice one showing how refraction, the mechanism of refraction, specifically with electrons, when electrons are passing into a material. And that is very critical when it comes to dynamical diffraction theory. Got a book coming out shortly, An Engineer's Guide to Nuclear Reactor Core Materials. Please get it if you're at all interested in materials. I think there's some interesting things that I bring out in that book that should interest young engineers and scientists who are in the field.